Oh, I'm sorry for being late. Yeah, let's just get going, Hello.
Hello.
Hi,
Yes.
hi. How are you doing? Good.
Hi. Yeah, I'm doing good.
No, good. So let's just get going, about control, and then we talk
Yeah.
about the lab. Yeah. Maybe you give me some background about, the knowledge.
Yeah, you can see my screen, right?
Yes.
Okay. Now, thing is like you have shared me the PDF, right? Like, what is the more information you needed here? Like, you have shared me two PDFs. Okay. Yeah, this one and one more. Okay, I think this one. So here you tell me like you want me to explain the mechanical part or the electronics part.
The mechanical part, the heat flow and the thermodynamics, all those kind of things. You just let me have a better understanding, how to,
Okay.
what's the function, what's the principle, working principle. Because you just give us a
Okay.
heat
Okay.
flow. I just go to the lab, and I'm gonna be a little bit, disarray. I want you to, clear out me those doubts, and then maybe just teach me a little bit about heat flow, because I checked some YouTube video and they're not very helpful.
Ha 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 ha. Okay, okay, got it. Okay, so I got it. So here I think we'll start. Okay, I'm audible, right? I'm audible.
Yep, you are audible. I can hear you very clear.
Yeah, yeah, yeah. Now, the first thing. Okay? Yeah, I'll just see. Now, this is the setup of the experiment. Okay, the heat flow experiment. So, uh, uh, I'll be telling of 50, 15, and 10 centimeters. Okay, 50 is this length. 50 is this length. 15 is the height of this
So you're not very clear. So
one,
you are
and
your
10 centimeter is the
internet
thickness. Are you getting what?
internet is not very stable. So hello.
Yeah, now it is clear.
No, no, no. I can hear you. Yeah, now it's better. Slightly better. Yeah.
Now it's better. Yeah. Okay. Yeah. So basically, this is a Quenzer heat flow experiment setup. Okay, this is the experimental setup. Okay,
Okay.
so they
Okay.
have given the dimension of 50, 15, and 10 centimeter. Okay, okay. So
Okay.
50 is length. 50 is the length of this machine. Okay, 50 is the length.
Okay.
15 is the height of this machine, 15 centimeter, and 10 centimeter is the thickness. Are you getting this
Mm,
one?
yeah.
So got it. What are they talking about height? And they have said it as 1 minute. I'll move this one up. Okay. Okay. Where is annotation? You got it, no? Uh, the length, the height, and the thickness. Okay. So actually, if this is a box, okay, they're talking about 3D. Okay. If I'm talking about a 3D thing, height, length, and thickness. You got no? You got
Mm,
it. No, this one. Okay.
yes.
Now this one. Okay. What they're telling it is like it is made up of fiberglass. Okay. This full component is made up of like fiberglass. Okay. This full setup. You can see a glass here. You can see this glass.
Yes. Yes. Yes.
It is made up of fiberglass. Okay. And inside this, there is a heater and a blower. Okay, there are two things now inside this. One is the heater and one is the blower. Okay, so what is a heater? What is a blower? I'll let you know. Okay, 1 minute. I'll close this WhatsApp. Yeah. Okay, so heater is nothing but it takes electrical energy. It is just a coil, copper coil. It takes electrical energy and heat this device. Okay, heater is a device. It is like a copper coil. Okay, when you give electric energy to the heater, it will give heat energy. It converts electrical energy to heat energy. Getting what I'm saying?
So heater is like induction heating. So it's like electrical energy, and
Yeah, yeah,
then
yeah. That's what. And blower is nothing but it is a fan. Okay, it is a fan. If you give electrical signals to the fan, it just rotates and it gives us the wind, hot air. Okay. For example, you know, fan.
Yeah, I know fan. Yes, of course.
Same way. Blower is also the same thing. You know, hair dryer.
Yes, hair dryer. Yes.
Hair dryer is a blower. Okay, one type of blower. Okay, where when you on the switch, we get hot air.
Yep. Yep.
And we dry our hair. Okay, so there are two things here in this setup. There is one heater and there is also a blower. Two things. Now the third thing they're telling it as there are three sensors. Okay, there are three sensors kept here. Okay, I think there is a big diagram here. Yes, here is the diagram. Okay, it is clear
Okay.
now. Okay. So look here, this is one. What is one? 1 minute. One is the base, very
Uh-huh.
basic. Two is the fiberglass. I told you. One is the base. One is the base. Two is the fiberglass. I told you this is a glass. Okay. Now coming to three, blower and heater. Where is number three? Blower is also kept here. Heater is also kept here. See, it is kept parallelly.
Okay.
Getting?
Getting yes.
Okay. So blower, it takes the air from outside and it will push here. And heater will blower just take the air and push it inside. This heater will heat the air and pass it on here inside this
Yep.
chamber. Okay. Now we have how many sensors? We have three sensors here. Okay, 5 6 7 other temperature sensors. See, this is temperature sensor 1, temperature sensor 2, temperature sensor 3. Three sensors. Ah,
Okay. Yeah. I can.
okay.
I can see that. So temperature sensor, yes, and then 8 and 9 is a on and off switch.
Yeah, here you can see 8 and 9 off and on switch. Yes. Then
Power
all this.
cable.
Okay. Now this 10 11 12 13 are like input and output of the sensors. Okay.
What is the sensor one offset? What does that mean? You know.
Okay. Where is that? 1 minute. This is done. Temperature 1 connection, temperature offset, temperature 2 temperature offset, temperature 3 temperature offset. So it is like what you know here. Okay, offset in the sense it will give the two datas. Okay, it will give the two datas. 1 minute. We have temperature sensor 1 offset. This is just a connection to one side, and this offset is like it will give an temperature details of how much is the temperature range. Okay, 1 minute. Mhm. Okay. It is just a nothing. What is that? You know, it will let us know that to adjust the room sensor. Okay, the one is the sensor, one is the offset. Here we can adjust the sensors temperatures.
So it's just adjustment.
This one is just measure the upons. Offset is to measure the sensor to adjust to increase or decrease the temperature. Okay. Next, the fan again the fan connections. Okay, again same thing. Fan connectors. Okay, so here there's a fan. Done. So this is basically a setup of the whichever you're doing experiment. So this consists of a fan. Sorry, it consists of a blower. It consists of a heater. It consists of three temperatures, and it consists of temperature changing things also, and to detect the temperatures and on
Okay.
and off switch. Done.
Okay.
So
Done.
this is
Yes.
now again in the detail view they're showing. See, all these things. Side view they have done. Okay,
Yep.
side view is done. Now specifically each components. Okay, each components they're telling it in very detail. Okay. Yes. Okay. Now one more thing I wanted to add it here. Okay. Now you can see here. And it has built-in amplifier. So what happens? Amplifier is a device which is used to increase the power of the heater and the blower. It is
Oh,
having a
okay.
small amplifier which will increase the power of heater and the blower. Okay.
So you can amplify the signal, amplify the power.
Yes. Okay.
Oh, okay.
Now the power delivered to the heater and blower are controlled by signals. We have to control the heater and the blower. We are controlling this by analog signals. Okay, we are sending the signals to the heater and the blower. That is why we are controlling the speed and the heat. What does the heater should deliver to this one, to this setup? Okay.
Yeah.
Now tachometer is a device which is used to know the speed of the fan. Okay. Tachometer is nothing but it is like you have a bike. Tachometer will be placed at the front. Okay, so when you go, your vehicle will be moving. No, so
Yep.
it will detect the speed.
Yep. Absolutely.
It will detect the speed. So tachometer is also a device which is used to measure the speed of the fan.
Yep.
Okay?
Yep.
Tachometer
Yep.
is like a light will be passing, so that when fan rotates, it will count how many rotations, then it will give us the reading. Okay, yes,
Okay.
done.
Done.
So this is all about the experimental setup. Okay, now here they are exactly telling which type of sensors is used here in this setup. Okay, so you can see here they have used a model of this one and a platinum sensor transducer. They are using platinum temperature transducers, okay, to measure the temperature. And the sensor's output is 0 to 5 volts. They're talking about the capacity of the sensor. And they are telling it as the sensor repeatability, means if you just change and off and on, off and on, off and on, it will have an error of plus or minus 0.1 degree Celsius. Okay,
Okay.
so this is all about technical details about the specific sensor which they have used. All the three sensors are same. 5, 6, 7 are the sensors, right? This is the main sensor topics they're telling. Okay. Now they're telling it as like how to calibrate the sensor. Okay. How to calibrate the sensor. Simply if you keep a sensor and it is showing the results or no, we'll not know. No. So before that, we have to calibrate the sensors. Okay.
Okay.
So this is a procedure to calibrate sensor. Okay, now I'll tell what is a procedure to calibrate the sensor. Okay, so first thing, what you need to do is turn on the heat flow and let the blower run for 2 minutes. Okay, first we need to on the heater as well as the blower and
Oh
run it
no,
for
so
2 minutes.
I think this part's fine. I
This
think
part is fine.
it's
You
fine.
can read
Yeah,
it.
I can
Ah,
read it myself. It's okay. So I think we just better going to pre-lab. There's a
okay.
part of the pre-lab. I think we can
Ah,
just talk about the detail about that.
okay.
Maybe
Pre-lab, okay. These are the specifications of that.
yeah,
Okay,
yeah. I will read it myself. I think it's okay. Data
okay.
acquisitions, or
This one, NI take acquisition system.
yeah, important. Basically
No.
measure all those things, analog to digital, right?
Yes, analog to
Analog.
digital. Yes, you
Yeah,
can
there
see analog.
must be DAC and ADC, because
Hmm.
that's how things operate,
Hmm.
Because so most of the things we get is basically all analog, right?
Hmm.
All the values for these sensors. So we have to convert it to digital, and then from
Hmm.
digital, and then you can read all those data from the
Hmm.
computer,
Hmm.
generate the result. I assume.
Hmm.
Am I correct? Am I saying this correctly, or
Yeah,
is
can you tell me again? Can you tell me? Can you
yeah?
repeat?
So most of the things with sensor we get the data, and then data is analog,
Hmm.
and then analog we get from the analog, and then we convert to digital,
Hmm.
right? And then and then the digital data, and then the digital data, and then we need to do all those things, right? Digital, and then we can choose
Yes.
simulation.
Yes, simulations. Yes. Okay. So basically, what happens is did you use the Labio or MATLAB? Did you use that thing?
I think we have to use the physical things as well as the MATLAB. I think both. I think we get some result, and then we use MATLAB to do some of the
Yes.
things.
Now, what does MATLAB does? MATLAB instead of MATLAB will not just give us the just one animation. Okay, LabVIEW is a software. What it does is it will have a National Instrument DAC device. Okay,
Oh,
when you
LabVIEW, yes, correct.
LabVIEW, when you give the signals in the LabVIEW, real signals will be generated from the DAC. Okay.
Oh, okay.
Okay, for example, you give sine wave of 5 volt. Okay, just give in the model, you just give 5 volt, but actually
Yep.
5 volt will be generated in the national equipment and it will give to the device.
Yep.
Okay, that is the DAC. Okay, that is data acquisition DAQ. Okay, so this I think these are the steps. Okay, following steps to connect. Now they're telling how to connect this to the devices. Okay,
Yeah.
cables. If we read this, it is very easy, man. We have to have the setup here. I think this setup, see.
No, it's
Uh,
okay. I think we can read all the setup during the lab as well.
we can read, and by we read if the device is in front of you, you can just connect it and
Yep.
you can read this and it's like one is they're telling first is for the temperature, second this is for
Yep.
the one more temperature, this is for one more temperature, three connections for temperatures. Okay,
Yep.
first two connections are for first is for the blower, second see first is for the blower, second is for the
Yep.
um, blower and heater. Okay, that's what they're telling about. Okay, so this PDF is this much only. Okay, yes, wait,
Yes.
this is this much only. Now we'll open the second PDF. Why this image have been blurred? Do you know why this has been like closed?
Oh, I guess they don't want you to, they don't give you a solution. They want you to calculate and all those things. Maybe that's why they want to do it.
Okay, okay, okay.
Because it's student workbook, isn't it?
Mm-hmm. This is the same thing. Okay, yeah. Okay, now here, yes, here, I think this is the same part. Okay, this is the same part which we have completed. Okay,
Yep,
now,
yep.
now here they are using the model called as bump test model. Okay, one Simulink model called as bump set method.
Okay,
They are
okay.
using this method.
Can you elaborate a little bit? What is a bomb set method,
Okay,
bomb
now,
test?
okay, bump test. Okay, so this is one of the model, okay, which is used for this, which is thermodynamically used for this system. Okay, this is just one of the type of model, okay, which they have created for looking at this setup. Okay,
Okay.
this is like thermodynamic model, okay, where you can sense the temperature and all. There are many more models. Okay, there are many models. So what happens is we will not get the temperatures or the gas or any air, any air movement or any temperature movement or any heat movement is there. We use pump set methods.
Okay.
Okay. uh, okay, now what happens is, now here uh, they are telling it as we are using PID controller. Okay, we are using PID. Do you know what is PID full form?
The integral
Proportional, integral, and differential. Okay,
differential, yes.
yes, we are using PID algorithms. Okay, we are using PID algorithms for the model. Okay,
Yep,
see,
yep.
I'll tell you now. You'll understand what is this bound set. I'll go down and I'll explain you what is this more. Okay, so now, yes. So now, see, what are the things here we should know? Okay, in this laboratory, first thing, derive first order transfer function of the model using bump set. So we need to create a transfer function. We should make a model for this using this method. Okay, second, they are telling it as on off scheme using relay switch to, because we already told you we need to change the temperatures, so we are also implementing relay. Initially relay will not be there. Second one will introduce a relay switch so that to control the temperatures here. Okay, third
Yep,
one,
yep.
we need to design this proportional integral controller. Okay, mainly and you can see, to mainly it is to regulate the temperature. We need to design this three things. We need to do, first one, we need to know what is the mass of this one, what is the heat transfer, what is the velocity, what is the volume. All this, by this we'll create a transfer function for this model. Then we'll introduce a relay switch. Then we design an PID, okay, proportional integral differential controller, to control the temperatures. Okay, done. Okay, now again they are telling it as the same thing. Okay, what are the prerequisites you need to know in order to carry out this lab experiments? Okay, first one, they have told it on writing and operating procedures for heat flow. I told you, you should be knowing the basic of what is blower, what is heater, what are the temperature sensors. That's it. And what is fiberglass. Done.
Okay.
Second is the transfer function. We need to make, I'll tell now how to make the transfer function for this, and designing of PA. Now whether did they give these things for you, whether did they send these
No,
files
no,
to you?
no, they didn't send me the file, no.
Okay, actually these files they have to send. If you open these files directly, the model whichever is there, we can open that model. Are you getting? Directly if you click this one, Simulink model will be coming.
Oh,
This
I think if we just copy this, paste this, and then into Simulink, this file will come up.
this file.
Uh,
Oh, I don't know that. We'll see. Okay.
yeah, it's probably building or something, but we'll see. Yeah,
Hmm. Yeah. No.
this is a pre-lab. Yeah, this
Yeah.
is a
Pre-lab. You want to start from here. Okay.
yeah.
Okay. So now, first one, explain how the model heat flow plant. Explain how the model is the heat flow plant. Percentage overstood, peak studied, control two regulators. Okay. Now I'll be here. Now first step is the to model. Okay. First step is the how to model this heat flow experiment. Okay. Hmm?
Yep,
Yes. Okay. Now, this is like related to mechanical. So here we are using a thermodynamic model. Okay.
yep.
Thermo. So which are the two main components you tell me here, which are using here? Two main components.
blower and heater.
Blower and heater. We have added a blower and a heater here. Okay, and now this is both are going into one chamber. Okay, we have denoted by PS. And now here, now you can see here UB and UH. Okay, UB and UH are the internal energies. These are like mechanical. Okay, when it goes into the blower, this mechanical energy is getting converted into voltages. Okay.
Oh, okay.
Here the mechanical whatever is there in the blower, that we are converting into voltage. So the input is mechanical energy, output is voltage for the blower. Same way for the heater. Here the input energy, whatever the heat is there, that we are connecting into voltage. Okay, see this both voltage will come inside the chamber, and this we are calculating. Now this both will heat this chamber. Yes or no? This both will heat the temp, and this is the output. Y is the output. You can see here Y is the output. Okay, now TA is nothing but the ambient temperature. Okay, ambient temperature means the room temperature. TA is nothing but the room temperature, and we need to measure what is the temperature inside the chamber considering the ambient temperature. Are you getting it now? What I'm saying? First one, we have the blower and a heater. The internal energy of the blower, that is mechanical energy, is getting converted into electrical energy, that is voltage. Here also the heat energy is getting converted to the voltage. Okay, these both are going into a chamber, and that is delta T is the difference. Okay, the change in the difference, and output is TC. Output is Y is equal to TC, and TA is the ambient temperature.
TC is the temperature. Temperature of the chamber.
Which one?
TC.
Yes, temperature of this chamber.
Okay.
Okay, 1 minute.
What's wrong?
1 o'clock हो जाता है मीटिंग फिर तुम्हें जा कर मैं बाद में जाता हूँ पीछे जा ठीक है ओके हाँ yes sorry man yes now we can hear.
Yeah, I can hear you. Yes, good.
Yeah, okay, so it is like PS is this delta T is the change in temperature of this chamber. Okay, now what happens is TA is the ambient temperature. We need to check the effects of the chamber with respect to the ambient temperature. You're getting, we need to check this one with reference to the ambient temperature. We are measuring the difference.
Yep.
Okay, so now here how did they design this one? Okay, see now the temperature of the chamber at sensor N can be described as VH is the voltage of the heater. VB is the voltage of the blower. TA is the ambient temperature, and XN, okay, XN is nothing but the distance between the sensors and the heaters. The distance, the place. Routing to what are the things? VH, the heater voltage, VB, the blower voltage, TA, ambient temperature, and XN is nothing but the distance between the sensors. Yeah, I think you have seen the image now. Where is that? Yeah, distance between the sensors. XN distance.
Oh, okay.
This
Understood.
Distance. Understood?
Yes.
Very good. Okay. So what is happening is now for this purpose, now this is the equation. Okay, this they have derived it. Now they are telling it as like for designing the temperature control, a simple first order transfer function model will be sufficient. They're using only first order. If it is not possible, then need to go to second order. Then again, if it is not proper, then we need to go to third order transfer functions. Okay, so now this they have given directly. Okay, this they have given directly as considering as a first order transfer function. Okay.
Yeah.
No. What are these things now? What are this transfer function for this model they're telling? Okay, they're telling it as Kn is the steady state gain. Okay, I'll tell in the graph what is this. Okay, steady state gain. VH is nothing but the voltage here. Okay, the voltage of the heater.
Yep.
And tau n is the time constant. Like what is the time taken here? Okay, this is the time taken. And do you know we write s plus 1? This is basic in control engineering. We write s transfer function. This is transfer function s plus 1. Okay, we need to only focus on these three things, 3 units. Okay, Kn is the steady state. Tau n is nothing but the time, whatever they give it. VH is the voltage we obtain from this heater. Got it?
Yep.
No. Okay. Now, now we look at this setup. Okay. So now they are talking about this transfer function. What is the input and what is the output here? Okay, they are talking, if you give the input, what will happen here? Output. Look here. Okay. Now this is a simple test based on the response for stable system. It is carried out following way. Okay, now input is chosen, which remains input is rapidly increasing. Now see, this is the input. Okay, in x-axis we have time, and we y-axis we have internal energy. U is nothing but internal energy. Okay.
Yep.
Okay, so you can see at 5 seconds the internal energy is 1 at 25 seconds will increase the internal energy slowly. Okay, we're slowly increasing the fan speed or the blower speed. Initially we'll be having same minimum, then we'll increase the speed. So at this 25 second the internal energy is increased, then we are maintaining that to certain speed, then finally we are turning it off at 1 minute. Okay, so the internal energy is reducing. Are you
Yep.
getting what is happening? See, initially it was here when you turn on, when we 0 seconds the fan was on, then fan was running at a slow speed for 25 seconds. Then when we increase the fan speed, directly the internal energy got increased at 25 seconds. Then after that it got wait, for example, for some time it got stayed, then it is like again the time is increased, the fan speed is remained constant, and finally
Yep.
we turn it off, so it will come down. Okay, the internal energy comes down. Now what are this what is this graph? They're talking about the output. Okay, they're talking about y. See here, y. Okay, they're talking about this one. See now, delta y. Well, delta y. Okay, see now what when we gave the internal energy as 0. Okay, they have showed it here. Okay, when they gave internal energy as 0, what is this? When you give internal energy, so it was minimum. Okay, suddenly when we increased the fan speed, okay, the heater speed and the blower speed and the heat, there was a steady curve. Okay, this is the steady state curve. Okay, this curve is called as a steady state curve. Okay, now here also there is a difference. Now see, this was the maximum and this was the minimum. That is delta y. That is what they are.
So can we stop for 1 minute?
Yes, yes.
I need to do something. Sorry about this. One
Okay,
minute.
okay,
I'll be back.
okay, okay.
Yeah, let's continue. Hello. Yeah.
Okay, okay. Share screen. Yes, share. Okay. Visible,
Yeah.
right?
Yeah, visible. Yes.
Okay. Now, okay. So see now what the input was. This. Okay, the input was this line. Okay, the input was this
Ah,
line. We got the
yeah.
output in this way. In a curve, we got the output as way. So you can see there is a variation, the input and the output. Okay, there are some losses. Okay, that is here. See, this is Kn. That is the steady state. The curve that is called steady state gain. Okay, and Tn is the temperature. Means time constant. This is time, and this curve is called as a steady state curve. Okay, now here they have mentioned it. See. See now, I'll be telling. Yes, yes, yes. Look here, look here. Okay, now look at this one. Okay, the input signal u is steps begins. Now I told you the input signal u begins at time 0. Now the input signal has minimum value UH minimum, maximum value U maximum. Okay. Now the
Ah,
result and output will be y. If this is U max and initial value will be YO. See here, this one directly. They're talking about this one. They'll be if this both are 0, this will also be 0. Okay. Suddenly, then what we do is we increase one step. That is, we increase one step. So suddenly, what happens is this output will change. The output will change. Okay, look here, look here. So they have represented by output by input. K is equal to output by input. They have given as
ah,
delta y and delta u. Okay, now what is delta y? Okay, what is delta y? Look here. This is the output, right? This is delta y. So
yeah,
maximum minus minimum. So maximum
yeah,
means YSS minus YO. Look
yeah,
here. YSS minus YO. Done. Now
yeah,
delta u. What is delta u? Delta u is again this one. Change. Change in input. So maximum u max minus u minimum.
yeah,
Okay, so they have written u max minus u minimum. So from here, they have told it as for this model. Okay, the output this they have given directly. But I don't know where this they have given. They have not showed the reference, but they have told it for this is the equation for this model. Okay, this is directly they have given it. Okay,
yeah,
the output must be, they have given directly this one. Now we are considering the time constraint for this one. Tau, what is the value we're considering? T minus T now. This
yeah.
much we're considering for that. Okay. So this is all about the basic thing. Now you see this model. I hope you understood. This model you understood how this differentiation came here. What do we consider? But can you tell me now what are the things we referred here?
So VH is the voltage for the heater, and then VB is the for the blowers, and then TA is the temperature, the ambient temperature, right?
Yes. Okay. Then we have a graph. What happened to the graph? Can you tell me?
So it's like a step function, isn't it? It's like a very easy step function. So it's like shoot go up. It's a horizontal, and then just a step from between 25 and 30. So that's why it suddenly jump up, and then it's like the all the way to flat until then it's the and then to 50, and that's gone.
Okay. So then what they did was this they got it from here, output by input. What is the output? K is the factor, output by input. So they wrote it down and they bought this equation. Okay. I think yes. I think no. Now here the first order degree is done. Now they're doing the second order. Okay, second order system. What they're doing it of. There is something called as open loop and closed loop system.
Yep, yep. This
Yeah.
is a unity feedback, right? There's no closed loop.
This is
Is this open loop or this is a no? I don't see any feedback. But this is
no,
that, but it's connect.
actually, what happens is this is feedback. See, whatever output is coming, it is going and comparing here. Again,
Oh,
it is
okay. So
sending. Okay,
so
this is
there's no negative feedback or whatever feedback,
no,
positive
there is
feedback,
no
negative.
feedback, negative feedback. Yes, but whatever value is coming, it is getting compared here and measuring, and it is come. Okay, so now generally they are telling it as it has a compensator. Okay, CS and a transfer function. They have placed the transfer function here, and output is Y. Compensator CS. Okay, transfer function, whichever we have wrote the transfer function. I think transfer function, which one? Transfer function. Where is the this is the transfer function. Okay, this is the
Yes.
transfer function for the model. Okay, and this is the output. YS is the output. Now what is happening is, now see here the output. What is the output? It is a multiplication of comparator, compensator, and the plant and the reference. What happens? This is a closed loop. So whatever the value it goes, it just compares and check the errors and come back. It will solve. Okay, so the result in closed loop transfer system. Always we get a closed loop. Now
Yeah.
they have just this ys was there, no, just put it down here so that this is a mathematical one. See, cprs was there, no, they put y. So when this y goes here, it became 1 plus this one. This is
Yeah,
just
they
like
move around, play around.
they put that ys that side. So it became, if you just
Oh,
multiply it down here, it will come the same one.
okay.
Okay. Now finally they got this. They made the equation as, instead of writing this fully, CSPSRS is nothing but k. Okay.
Yep, yep,
They made it as k, and 1 plus CSPS is tau s. So that is what they have written. CS and CP is nothing but tau. Temperature steady. Sorry, what is the temperature constant? Tau s is tau is nothing but time constant. Okay, time constant.
yep, yep,
So
yep.
then that much we have done, and here comes to the last one. Okay, after solving, after putting the values of the actual values of the after the compensator and transfer function, actually here they have not shown how the values are. Actually whatever that we have to substitute here, all the values here, then finally we got they have written it as, this is the equation. Okay, by solving all this, writing the comparative values, what are the transfer functions, by solving all this, uh, they have written here. Okay, this equation we are going to get. Okay, here we are talking about the vibrations in the system. Okay, omega n stands for natural damped frequency. Okay, there is something called as underdamped, overdamped, and critical damping. So omega n stands for natural damping frequency, and is zeta. This symbol is damping ratio. Okay, so by knowing these two values, by knowing this, what is the damping factor and the natural frequency, we'll get the output of this model here. This is second order.
Yep.
Okay, so much on this. I think from the next rest of the part, okay, rest of the part, your electronic HOD, like electrical faculty is going to take it. Okay, this is only the mechanical part. Till here is only the mechanical part. Okay, actually this control system also comes in that of electronics only. So I have explained it here only. Other faculty will be coming and he'll be explaining about the electronic components. Is it okay?
Okay, so you're done. There's another guy is gonna come in, or is
Yes, yes, I'll contact him. I think, wait, you need to contact. Yes, he's going to come and he'll going to explain this. Okay, this all are like electronic components. Okay, I told you, no, first component. Do you remember? The second thing was adding the relay. This was not there. Do you remember or no? The first steps I
I
told you.
know. Relay is a switch, right? Yes, I know.
Yes, yes. No, no, I told, no. Here, look, look here. He told you. See, first was here. I think this is here. It is this not here. There were three steps. First, initially we used to do directly, then we added the relay, then we added a, yes, where is that? Yes, yes, this was, first we had derived a first order transfer function for the model. Second was implementing relay. We're just adding the relay. Third one, we are designing the PID circuit.
Yep, yep.
Second, so this is the second relay. Yeah, same setup, we're increasing a relay switch. Okay, so again, how this working and all, so repeated. Okay, something
Yep.
called as hysteresis. Something called as hysteresis.
Hysteresis can change very fast.
Yeah. Yes, in the sense, what will be the input, output will be not be there. There will be a gap. Okay, there will be a
Yep,
gap. So that is called hysteresis. I think there is a hysteresis in this graph also. I think this all is transfer functions. He will be explaining. Okay.
yep, yep.
And see, actually, if you open this, I think if you open this directly, we'll get into William further. See, do you
Yep,
have
yep.
MATLAB in your software? Do you have MATLAB in your laptop?
I think I do, but it's I haven't updated for many years. I think
Okay,
probably not today, not today. Next
okay.
time.
See, but
MATLAB.
directly, if you have this, directly this model will come. See now, the blower temperature directly, the input
Yep,
voltage input of this temperature degrees, and we are checking that. And this is a converter, analog to digital converter, and the volt.
yep,
This is.
yep, yep.
So you're studying in which year actually? What is it? This is
Master,
a
first year master.
first year master. Which branch?
Electrical and electronics. So this is control is something they must take now.
Masters in electronics. This is okay, masters. Okay. You're from Canada.
Australia.
Australia. Okay, okay, okay. Okay, but here I think this one, all these MATLAB things, your sir will be explaining. Okay, no?
Yeah.
I told you, this is this from where actually this is a company, no? Your college gave you this or what? This is actually
Yeah.
company, no?
Yeah, they're using this. Yes.
Oh, okay. So I think I'll contact the sir 1 minute whether he's there or not. Can check. Hello, sir. Are you there?
Yes.
Adit- Aditya, sir. Yes, sir. Mechanical part. I have explained. Okay, we need that component like explaining of this one. We need electronic faculty. So
Okay.
what will you do? Hmm?
Okay. So after the lecture, we will discuss with the Jerry. Okay. So Jerry, do
Okay.
you have any doubt in the mechanical part?
Not really. The mechanical part is clear, sir.
Okay. So we will wind up the session now. Then we will discuss about the electronic part later. Okay.
Okay, we can end the session now. So how long is it? Did this session last an hour? So do
Yes.
we?
I will let you know. Okay.
Okay, thank you all.
Okay.